we're going to talk about protein ligand binding. So let me start with the outline. So try to recap why protein ligand binding is still a long-standing problem from the point of view of computational biophysics chemistry. And then I'm going to show you that there are two approaches, two routes to get to the same answer. One is purely alchemical, and the other one is purely geometrical. And then, so that's with the objective to get an absolute binding for energy, and or a standard binding for energy. And then we're going to move to the calculation of relative binding for energies, which are sometimes more interesting from the point of view of pharma, where they want to have a ranking of affinities. And then I will briefly mention Adenine Scanning, which is basically kind of a corollary of doing this for energy calculations to predict, stabilize a protein ligand or protein-protein complex by mutations. And then we'll go a little bit beyond protein ligand binding with protein-protein interaction. Okay, so let's start with the beginning. So it's been kind of a holy grail for theoretical and computational biophysics to get binding affinities, and so I'm sure that you've seen this kind of contraption. So you have a drug, or you have a target. And you're trying to find the best possible drug for that target. So you're using methods of decreasing granularity. So you start with very coarse grain approach, like shape recognition, and then based on the candidates that you have isolated, you move on to a more sophisticated approach like rigid docking, and then on to an even more sophisticated approach called flexible docking. And finally, on the very few candidates that you have left, you can apply expensive energy calculations. The idea here is that at every step of the way, you have a constant computational investment. So on the top of the funnel, we call that the screening funnel, sometimes high throughput screening funnel. On the top of the funnel, you do a lot of calculations, very fast calculations, just trying to discriminate the keys very roughly for a certain keyhole, whereas at the end, only a handful of calculations, but those are very expensive calculations. Back in the 90s, that was kind of the darlings of pharma. People in pharma saw that as a big promise that would solve everything, and to the point that people were convinced that it would be just faster to do that than just do the wet lab experiment. But of course, we know what happened, and the promises were not fulfilled, and of course, people in pharma, they're kind of dubious, and this method became kind of dormant in the pharmaceutical industry, the late 90s, early 2000s. And they were revived more recently with companies like Schrödinger and also efforts from people from academia like David Mobley, Michael Schertz, John Sierra, who basically say that there is still hope that this method will help discriminate between candidates. But what we need to do first is to gauge progress toward the goal of deploying a viable engineering tool. It is essential to establish standardized benchmark sets of receptor ligand system. So basically, and that's what forms the rationale for efforts like sample X, sample 1, sample 2, sample 3. Just like you have the CASP exercise, where you try to predict likely protein folds. In sample, you try to predict binding affinities. Like if you are protein, give you a number of drugs, and I ask you to rank this drug according to the binding affinity towards the targets. And so you give me your answer, and then you publish the results, and whoever closest to the correct ranking wins the prize. So that's nice. And what I'm going to try to show you is that you actually can get close to the target, to the experimental value, if you follow the correct methodology. So let me give you some perspective here. So that's what we're interested in. It's equilibrium, protein plus ligand. In equilibrium is the complex formed by the protein and the ligand. Our friend here in the first row, eating his breakfast, asked me, but can we access this binding free energy just from one brute force experiment? And of course, the answer is no, because it's statistically irrelevant. You have one event, and one event is like no event. It's like it's statistically meaningless. So in this example here, this is a movie actually from Gianni De Fabritis, who in 2011 looked at the binding of, I think it's trypsin. I'm not quite sure what it was, what protein it was, but that doesn't matter. It was a fast binder. And you notice also that this binder is very simple. It's actually a rigid molecule. So you don't have the complexity of potential conformational change upon binding. And so what he did is he ran, if my recollection is correct, he ran 500 simulations, out of which he did statistical analysis to infer the KD. You can actually get the KD, the dissociation constant, as a ratio of off grade constant over on grade constant. Something that you can access incidentally from experiment with Biophysics or glass non-surface resonance. Basically, the idea is you have proteins attached to a surface, and then you have this stream of solution with the ligands. The ligands will actually bind to the protein. You can measure K on, and then you wash that with another solution, the reft of the ligand. Then you measure the amount of ligand that unbinds, and you get the K off. So the ratio of the two kinetic measurements, stop flow kinetic measurements, will give you the KD. You can also get directly KD using ITC, isothermal calorimetry. So, bottom line, if you want to do brute force, just let me finish. If you want to do brute force simulation, definitely one event is not enough. You need to do multiple simulations to actually get a good feel of K on and K off. But that's, of course, limited by the fact that if you have a fast binder, it's very possible. So you get a good estimate of K on. It's very possible that you won't get a good estimate of K on. Then you'll do. Yes?
How do you define KD? KD is dissociation constant?
It's a dissociation constant.
Then what is the difference between KD and K off?
KD and K off. No, K off is a rate. It's a rate constant.
Isn't KD is K equilibrium?
Yeah, it's the equilibrium. Exactly. It's either, well, in this case, it would be Ka. It would be association constant. This is the definition of K. It's the ratio of K. That's what you see in every textbook. That's what you see in people doing this kind of experiments, like Alan Furch. You have tons of paper, and this is how they calculate KD. Dissociation constant.
It is the K equilibrium.
Yeah, it's an equilibrium, absolutely. Okay, so let's see that now from a theoretical standpoint. So this is my setting. Well, not what I'm going to do, what I'm going to simulate. We're trying to explain what we're trying to achieve. So I have a protein, and this protein is in a bath of ligand, and it's possible that one of the ligands is actually bound to the protein. So here's my equilibrium constant, which is like the concentration of the complex over the concentration of the protein times the concentration of the ligand. Let's expand this, introducing two probabilities, PO and P1. The PO is the probability that no ligand is bound to the protein, and P1 is the probability that the ligand is bound to the protein. So then I can introduce this P1 and PO in my equilibrium constant, and then further expand, introducing some configurational integral. Now I'm using this subscript here, site, to say that the ligand is actually at the binding site. One ligand is at the binding site, and bulk, meaning that the ligand is in the bulk. Okay. So in this case, the first term will be ligand 1 in this bath of n ligand. Ligand 1 would be at the binding site, whereas the other ligands, the n-1 ligand, will be in the bulk. And of course, that's normalized with all the ligands in the bulk. That's the first term. In the second term, it's ligand 2 that is bound to the protein, and the rest of the ligands are protein in the solution, and so on and so forth. But of course, my ligands are indiscernible, so I can factorize that. And the other thing is that I'm dealing with an homogeneous solution, so the concentration of ligand is nothing else than the number of ligands divided by the volume of the bulk. Last, I'm saying that if the ligand is not bound to the protein, it at some site x1 prime, far from the protein, so that it doesn't interact. I'm introducing that in the form of the Dirac functions here. Okay, so now here's my final expression of the equilibrium constant. And as such, there's nothing much I can do with it in terms of brute force. That's where Trinity calculations are coming into the picture. So I will show you now that we can follow two routes that are very distinct, in nature. One is an alchemical route, the other one is a geometrical. Yes, sir.
If we were to begin these, to try to get these binding energies from start to finish, do we have everything appropriately, the correct number of simulations? What is the wall clock time that we would be waiting for?
You're going too fast. I'm going to give you the timing and everything. Just bear with me. So let's start with the alchemical route. And one of the real pioneers in the field is Jan Hermans, who really gave a lot of thought about how to do this. This is going too fast, actually. I need to revise my animation. So so the idea here is we're going to use alchemical calculation in the spirit that we described on Monday, which is basically playing with the potential energy function. In this case, to uncouple or couple reversibly the ligand to the binding site of the protein. But now, imagine that we're trying to decouple the binding site. I'm going to hit this situation. I'm going to play that again. So we start with the protein here, the bound state. I'm going to decouple it to get the unbinding trinity. And the problem that you're hitting is the floating ligand problem, also known as the wandering ligand. As you uncouple the ligand of the binding site, it will start to, drift away. You may say it's not a problem per se, if you're just interested in the uncoupling, but remember that we want to do the simulation as a good practice. We want to do the simulation in both directions. So now, the starting point of the reverse simulation is kind of unknown. I mean, it's far from the protein, and it's pretty much like there's just a snowball chance in hell that it will recover the correct binding site and the correct binding pause. So we have a problem. So that justifies the introduction of a series of restraints. So here is again the reaction or the equilibrium we are targeting, and we want to get this quantity. So instead of getting this quantity directly and calculating, looking at the vertical legs whereby we're transforming the ligand into nothing, we're going to go through this step. We're going to first restrain the ligand. So 0 is actually the ligand unrestrained. So the star means that it's going to be restrained. By restrain, I mean restrained to its native conformation, orientation, and position. And only then, when it's restrained, we calculate, we uncouple it, or we couple it to the binding site. And we have to do the same thing, of course, in the law. And whatever restraint that we have introduced, what we need to calculate the free energy contribution to the binding free energy usually is restraint, because I'm adding a conformational restraint. It means that I'm removing some conformational entropy from the system. I'm adding positional restraint. I'm removing positional entropy. So all this configurational entropy, or this loss of configurational entropy, has to be accounted for in the thermodynamic cycle. So in practice, here's how we do it. So we do a double annihilation strategy or a double creation strategy. And I'm defining two computational assays, one for the bound state and one for the bulk state. So in the bound state, I have my protein, I have my ligand, and I'm going to freeze my ligand, and I'm going to introduce some groups of atoms to define a frame of reference so that I can actually define the relative position and orientation of the ligand with respect to the protein. I'm also freezing the conformation of the ligand in the bulk state. And only then I can make my ligand disappear or reappear reversibly. And all this contribution, adding restraints for the conformational degree of freedom, for the orientational degree of freedom, and positional degree of freedom, all of this is accounted by a series of integrals. And so I have here in salmon, pink, I have the restraint contributions in the bulk, in the bound state and in the bulk state. And here in green, I have the uncoupling in the bound state and uncoupling in the bulk state. And what you have here in purple, for the positional and orientational degree of freedom, you don't really need to do any special calculation. You can do that analytically because it's just a rigid body translation of the ligand. Remember that the ligand is coerced in the native conformation. So it's just a ligand that is tumbling and translating in a box of water that you can calculate analytically. So that's basically the theoretical framework for the alchemical ones. Now let's see the geometrical one. So for the geometrical one, again, I mean it's the same thing. So here's my complex, my protein, the ligand bound to the surface, and everybody, moving. But what we're going to do first is we're going to restrain the ligand in the conformation of the native state. And just like what we did for the alchemical route, we're going to define a subset of atoms. So that's forming a frame of reference, which will allow us to define the relative position and orientation of the ligand with respect to the protein, introducing the usual 3 Euler angle, phi, theta, and psi, the distance, and the polar angles, theta and phi. So again, what we're going to do here in the geometrical routes, we're going to do geometrical calculation, in other words, potential of mean force calculation, with respect to these different variables. And the way it works is very much like Russian nested dolls. So I start with my ligand completely unrestrained. And I introduce my first restraint on the conformation. So it will be a potential of mean force using as a collective variable RMSD with respect to the native conformation. Calculating the potential of mean force with respect to the native conformation. Once I have that, I'm going to restrain the conformation of the ligand to the native state, so imposing as a restraint that RMSD equals 0. And now I'm going to calculate the second potential of mean force, which will be the first Euler angle, and under the premises of a restrained ligand. Then I'm taking the minimum of the potential of mean force, they're all quadratic. I'm taking the minimum of the potential of mean force over theta, and I'm imposing a restraint on theta, and of course on the RMSD, and I'm calculating the third potential of mean force, and so on and so forth. All of this here until I reach the magnum opus of the calculation, the mean force, the most challenging, which is separation PMF. So now that everything is restrained, I can, along R, I can separate reversibly. And just like in the alchemical routes, I have these terms here in purple, which again corresponds to analytical contribution for the unbound states. So whatever restraints I introduce in the bound state, that's what you have to realize, that pretty much the bottom line of the philosophy. Whatever restraint I introduce in the bound state, I also need to introduce them somehow in the unbound state to balance out the thermodynamic cycle. Let me just give you an example here. Let's take the case of theta. So I'm calculating the potential of mean force of theta. So if you look at this ratio of configuration integral, what do they mean actually? So in the numerator, I have this term here. So I have a potential energy function augmented by a potential, harmonic potential on the conformation, you see. And here I have, actually I'm expanding this, I have U plus UC. And I also have here U theta, potential that I'm applying on theta. And so that you can see that you can isolate this, and now you're getting exponential of plus beta delta G theta. And it's nothing else than the integral, it's nothing else than of the potential with respect to Okay, so now let me give you a concrete example. So we to make our point cogent, we try this strategy on a test system for which the force field wouldn't be an issue. Basically, you sweep under the rug the force field, and you use as a ligand, you use a peptide. So it's a protein peptide interaction. With the leap of faith that the charm force field is doing a pretty good job with proteins and peptide, which is the case. So sampling is definitely the primary source of error in this case. And so the example is the SARC homology domain 3 of the tyrosine kinase ABL. And the binder is P41, which is a proline-rich decapeptide. binding at the surface. And so if you follow the alchemical routes, you find minus 7.7 kcal. And if you do the geometrical route based on these potentials of mean force, I was mentioning the quadratic nature of this potential of mean force, essentially for the Euler angle and polar angle. But at RMSD, they are a little bit more, they're a little trickier to obtain because of what I was mentioning the second day, that it's a degenerate variable, and of course you need to sample more to get a reasonably converged potential mean force. But those are like the difficult ones, the bound state RMSD, unbound state RMSD, and of course the separation PMF, which you see here. Those are very easy to get, a matter of a few nanoseconds, let's say 5 nanoseconds. RMSD, in this particular case, as much as 10 to 20 nanoseconds each. Separation PMF, maybe 50 nanoseconds. All in all, I would say 200 nanoseconds, a good estimate for this kind of system. So, minus 7.7, minus 7.8, an error bar on the order of 1.5 kT, experimental value minus 7.5. With experiments. One thing that I want to mention is, when do you want to use one method more than another? When do you want to use the alchemical routes? When do you want to use the geometrical routes? Well, it really depends on the kind of protein ligand system that you have. So when the ligand binding is very quote unquote superficial, the ligand is basically like resting at the surface of the protein, then I would say that they're equally good. They're equally costly. They're equally good. Conversely, if the ligand is buried in the binding site, let's say if a GPCR, like beta adrenergic receptor, and the ligand is deeply buried in it, then of course the geometrical route is not going to work for the reasons that I mentioned, that Jerome mentioned yesterday, of this orthogonal degrees of freedom that will stymie the extraction of the ligand from the binding site. So in this case, you want to use the alchemical. Other than that, they're just as easy or tricky. Depends on what perspective you look at that. Yes?
Are there cases when the alchemical route is not as useful as the geometrical route, or would be a less appropriate design?
In which case?
I'm asking if there are cases, like you mentioned how with the superficial ligand binding, either one would be appropriate, but if it's buried, only the alchemical one would be appropriate. Is there ever an instance that you've come across where the alchemical one is not appropriate, but the geometrical one is better?
Well, the only thing I can think of is when the ligand becomes really bulky. And let's go all the way to super bulky protein-protein interaction. In this case, you would be brain dead to do a chemical transformation, because that would be like a huge perturbation to remove an entire protein. I mean, imagine the amount of reorganization that the solvent around the protein upon the perturbation. So in this case, of course, protein-protein interaction precludes alchemical transformation. There is another instance where you want, but that's more practical. I'm going to come to that in a minute. Why do you want to use geometric? Is now we have, as you can, surmise from the previous slides, there's a lot of bookkeeping when you do like this Russian nested dolls. Now we have all of this automated, so you don't need to do the all the bookkeeping, and so in this case, geometric would be advisable. Yes, was it Bryce or Brian?
I was just going to add that also when the ligand's charged.
When the ligand is charged, yes, maybe you want to use the geometric. I mean,
Especially if it's strongly charged.
yes. Well, you're right. You're right. So this is like, yeah, I regret that Benoit is not here, because I mean, so Benoit is a kind of a proponent of doing this. When you separate, you want to do this Poisson-Boltzmann correction at large distance, because evidently you may be, if it's strongly charged, you may be missing one of the 1 over r squared or 1 over r in the long range interaction. So you need to account for that. Yeah, I'm not sure. I'm not sure that. I think that it would be equally, but it would be more straightforward to do the correct post-treatment, the Poisson-Boltzmann post-treatment, if you do the geometric transformation. Okay, so so far, yes, sorry.
So when you say sampling is the primary source of error, do you mean, what do you mean?
What I mean is, the reason we chose this example, to illustrate the strategy that we put forth is we didn't want the force field to come into the picture. Force field, especially additive force fields, are notorious for not being, optimal. By no means this should be construed as bashing the efforts of people like Alex Mackerel. But we know that they're not completely foolproof, and that if you're dealing with drugs and very exotic functional groups in drugs, you can have surprises that the force field is not completely optimal and lead to big deviation from the experimental binding fidelity. Whereas in the case of ligands, I mean, we kind of suppose that the charm force field is pretty good. I mean, it's already it's been amply tested by the community, and so we chose that example so that the force field doesn't come into the picture. That the main source of error is the method in the sample. Otherwise, you could say, well, maybe, it's more difficult for a referee to say, well, this good agreement might just be fortuitous, compensation of error in the force field, but because you're using the same force field, the charm force field for protein and ligand, it's less likely that it's completely coincidental that we get this kind of an agreement. Now you can say, well, yeah, but you have a pretty big error, but that's c'est la vie. That's life. I think the reason we have this large error, of course we could dissect how to calculate the error. This is probably a very conservative estimate of the error. But you have a lot of sources of errors. I mean, if you take the geometric plot, you have all these potential inputs. There is an error on each of them. You have to add. And of course, we're making this supposition, this assumption that the errors are kind of independent, so that you can just take the square root of the sum of squares. It's true and it's not true. Okay.
Question.
Yeah.
How do you calculate the errors? You repeat this a couple of times?
No, we so for the alchemical routes, we take a very conservative. That you can criticize as much as you want. Please. we just take the we get the error from the hysteresis between the forward and the backward transformation. For the potential of the mean force, there is actually a formula, propagation of error, which I showed on the first day, which involved the calculation of correlation length of the time series, and yeah, which is based on the calculation of the variance. That is when you can ask your own, he has his own idea about calculation of errors, and sometimes you're so almost tempted to not give an error bar because they are so controversial in a sense. That's we know that the data is highly correlated, and we do whatever we can, but I still think that these values of this estimate of the errors are pretty conservative. Anyway, so there is, I mean, as I showed on Monday, there is actually the formulation to calculate these errors. For ABF, there is definitely, that's the word, Eric Dar, error probability, and for FEP, there is also, I mean, I showed that, for the Bennett acceptance ratio, there is an estimate of the statistical error, which still misses the systematic part. The systematic part, there are papers from the group of Tom Wolf where you try to estimate. What we do is we just prefer to give to overshoot the error by just taking the hysteresis. Usually, if you take the systematic error and the statistical error, you add them up, it's usually less than what you get from just looking at the hysteresis between the forward and the backward.
How expensive are these calculations? Like
this error calculation?
No, this can like if someone wants to repeat them.
So yeah, we've done that also. That's well, I mean, typically for this kind of system, so the SH3 domain with one of these peptides, these decapeptides, that's about 200 to 300 nanoseconds.
So it's not bad.
Today, no, it's pretty cheap actually. You use GPUs, not for FEP because it's not yet available in MD, but for the geometric route, you can use GPUs. It's pretty cheap. Okay, so thanks to the Kohlmann's gurus, we made these calculations a little bit easier to handle. So in the past, you had to, until very recently, you had to define these groups of atoms that I was mentioning to basically define the relative positions of 3 groups of atoms in the protein, 3 groups of atoms in the ligand, so that you can define a frame of reference in each of them. These 2 frames of reference are used to basically define the relative orientation and position of the ligand in the protein. Well, now we don't need to do that. So we have recast the different variables that we use, the Euler angles, the polar angle. The only thing you need to know is the center of mass. Just deal with the center of mass of the protein, the center of mass of the ligand. And all of this is done in the form of Kohlmann's scripted functions that you mentioned yesterday. Actually, that's true for the Euler angles. For the polar angles, it's actually hard-coded in Kohlmann, so you can actually invoke the variable directly. And the way you're going to do these simulations is extending Lagrangian form of equilibrium. And so I was mentioning the good news. So the good news is that you can even be lazier. So the thing is, this afternoon you're invited to do a tutorial. Maybe some of you already started to work on that, which basically takes does it the old-fashioned way, so with the definition of the user diagram. But if you really want to be lazy and do it faster, you can use this, which quite unfortunately didn't make it. Is not in the version that is available on the website, the TCG website. So you'll have to download separately the GUI and place it in the proper directory in the VM distribution, and then source the GUI. I can show you how to do that. But then you have this GUI, and you need to invoke it twice. You invoke it for the setup. So for the setup, it's going to ask you PSF file, coordinate file, velocity file, XSC file of an equilibrium simulation of protein ligand complex. And it will also ask you the same thing just for the ligand. And then it will generate for you. So we're talking about the geometric route here. I'm sorry. It's only for the geometric route. It will create for you, it will generate for you in different subdirectories all the input files, the covars input files, and nav input files to do your different potentials of mean force calculations. So I don't know if you counted, but you have to do 8 potential mean force calculations to do the geometric route. So you have so you have the RMSE, the bound state. You have the 3 Euler angles in the bound state. You have the 2 polar angles in the bound state. So that's already 6. You have the separation PMF from the bound state to the unbound state. That's 7. And then you have the RMSE in the unbound state. So that's 8. So you'll have, in your directory, you'll have 8 subdirectories. And now it's ready to run. So you just have to upload that on your server or even do it on your laptop, your last laptop. And then once these calculations are done, then you invoke the GUI a second time, but this time to do the analysis. You see you have your setup, and here you have analyze. And now the only thing you have to do is specify where the potentials of mean force are. So the .pmf file, either Caesar or UI.pmf. You have to provide also the force constants, which will be used for the post-treatment. You remember this convoluted integrals, configurational integrals. You need to specify what were the force constants that you added to restrain your ligand positionally, orientationally, and computationally, and the temperature, and it will compute for you the binding frame, and the job is done. In the past, what you would have to do is take one potential mean force at a time, go to XM grace, do the integration in XM grace, divide by the potential mean force plus the force constant. That is also with a integral in XM. It's pretty tricky. Lots of bookkeeping. So it's really fast. Makes your life easy. Okay, so now that we're done with the absolute binding energy, let's move on to relative binding energies, which are in principle, traditionally, they're easier. So this is, so you can see them from 2 perspectives. You can see them from the point of view of alternate guests or alternate forces. So if there are alternate guests, which is the most common situation, you have the same protein, but you're comparing the binding affinity of 2 ligands towards that protein. So the absolute binding free energy, doing the absolute binding free energy calculation will give you that quantity. But we're not seeking that quantity, we're seeking the difference between that quantity and that quantity, which is equal to the difference of the alchemical free energy at in the bound state and the alchemical free energy in the unbound state. So basically, what we're doing here is we're mutating ligand A. And in principle, we don't need to add any restraints. I mean, if we deal with a congeneric series of drugs whereby they all look alike, they have the same scaffold, they only differ in the form of a small ornament on that scaffold. It's a CH2Cl becoming a CH2OH. Those are like pretty small perturbations. And in principle, we don't expect any change in the binding point. And therefore, there's no real need to add any restraint in the calculation. So in general, it should be pretty easy to carry out and to converge. And you can imagine that instead of changing the ligand, you're changing the host. What's the effect for a given ligand? So this is what you see here in the background. I'll explain to you. It's a study that we did in 2013 where it was very fashionable. 2012, it was very fashionable to work on H1N1, avian flu, and people were trying to understand what's going on. I mean, I thought that Tamiflu was effective, or Vilanza was effective, but of course, the neuraminidase had mutated in the meantime, and so the two drugs that were effective on one of the early version of neuraminidase was no longer effective, and so to understand that, what we did is look at mutation of neuraminidase and showing indeed that the enzyme was becoming kind of impervious or resistant to one of the two drugs. Okay, so that's good, but I'm going to show you now an example where, kind of a counterexample, where doing relative may not be the best option. And for that, I'm returning to the case of the SH3 domain of Abel tyrosine kinase. And remember, I was dealing with P41. I'm dealing with P5, which, and I'm an ass, I forgot P41. But it differs from, you might remember here we had an extra protein. So the difference with P5 is in these 3 amino acids, or these 4 amino acids. We have 1 protein less. I think here we had instead of a threonine, we had a serine. Anyway, so they differ by 4 amino acids. And so what we did is we transformed P41 into P5. So on the one hand, we did the absolute binding free energy for P41. See the previous slides. We did the same thing for P5. Actually, for P5, if you do with the geometric route, you get minus 5.5 binding. The experimental binding free energy is minus 5.52. It's pretty good. And so, if you remember the previous slide, we had found minus 7.8. So we have 7.8, 5.5, so that's 2.3. If you do the alchemical transformation here, so getting relative, mutating P41 into P5 in the bound state and the unbound state, you get 0. That's at the price of 697. Now, if you double the time, which we did, so we went all the way to 1.2 microsecond, get 0.9, you're still far from the 2.3, the target 2.3. So we stopped at that point. Maybe we should continue and add more sampling just to see if there is an asymptotic behavior that you can add more and tend towards. But in this case, it would seem that it's more cost effective to do the absolute binding frequency calculation. Now, you may argue that maybe we were brain dead to do the perturbing the 4 amino acids at a time. Maybe it would have been more cost effective to mutate one amino acid one after the other. It's very possible. We didn't try that. So we just did, change the 4 amino acids at the same time. Okay, so adenine scanning. So adenine scanning is something that actually was born in one of these workshops. And so we have a plugin available in VMware. And it was born in one of these workshops actually in Atlanta in 2014. We have more and more people from the experimental world coming, attending this workshop. It's the general workshop, not the special one. And they wanted to know, they wanted to do this adenine scanning experiment in silico. But without the need to learn statistical mechanics and really have a deep understanding of how to run the simulation. And so that's what we did, or we tried to do. So you can use adenine scanning for 2 purposes. You can use adenine scanning from the standpoint of predicting stabilization or destabilization upon replacement of amino acids like alanine. So the way you do it usually is you take your protein ligand or protein-protein complex, and specifically you look at the binding interface. So at the hotspots, what are the amino acids that contribute to the binding, and you replace them by alanine. And so that's what you have here in the plugin. So you have your sequence of amino acids, and you have the amino acids that contribute to that are part of the interface, the hotspots amino acids, and those will be transformed into alanine. So basically, you follow this. So you're not calculating the absolute binding frequency for the mutants and for the wild type. You're actually doing the mutation in the unbound state and in the bound state. So in this case, we are replacing one amino acid here in the protein. You can also use adenine scanning for so-called thermal shift assays. So to predict the again stabilization, destabilization, but just the protein, not a complex, but a protein upon mutations. So you would have like some call that a folding energy to go from a unfolded state to a folded state for the wild type, and a folding energy for the and so the kind of thermodynamic cycle that you would have and that people are traditionally using is they consider the mutation in the entire protein, and they consider the mutation of a tripeptide, so the central peptide in a tripeptide. That's pretty common. I've seen also pentapeptide. I don't think I've seen a single one, but I've seen most of the time it's tripeptide. And so you basically ignore the rest. You suppose that the rest is kind of important to the extent that these amino acids don't interact with the amino acid that you're trying to use. Kind of isolate. And so what you will do with the GUI is prep the simulation for doing this mutation, so delta G0, and delta G1. So just like the GUI for absolute binding to energy in the geometric route, you have to invoke the GUI twice. You invoke the GUI to set up your energy calculations of the different mutations. So it will, tell you what are the hotspots, give you the sequence of amino acids, and then you can override, say, well, I want these particular point mutations to be carried out. It will prepare the files, all the files. Then you just run different simulations. So you have like subdirectories for each point mutation. And then you invoke the GUI a second time to do the analysis for energy perturbation calculation. Now, what was on the what the experimentalists wanted to have is a tool that also helps them interpret or kind of assess the quality of the calculations very easily. So as you can see here, the way we present the results, so we have the sequence of amino acid. We give here the free energy for the host guest and for the host. In this case, the host, we're mutating proteins, so it's the host that we're mutating. So you have the two. And we put a little traffic light. So the traffic light is green if we think that the calculation is properly converged. How do we do that? It's very rough estimate based on the forward and backward hysteresis. So if we have a hysteresis of less than kT, we put a green light. If we have a hysteresis between 1 kT and 2 kT, we put a yellow light. And if the hysteresis is more than 2 kT, we put a red light, which is the case here. Actually, we have 5.1. So that's a good, it's a red flag telling you that you better rerun that particular simulation. And then on the right-hand side, we have like this color bar that will tell you if the replacement into an alanine is favorable to stabilize the complex or unfavorable. So you see here, we're going from minus 2 kcal to plus 4. So these replacements here in blue, dark blue, will be favorable. It will be conducive to stabilization of the complex. Whereas the one in flashing red means that it's an unfavorable point mutation, or unfavorable replacement by alanine. Okay, so now let me finish, unless you have questions. So let me finish with beyond protein ligand binding and moving to protein-protein interaction. So you might remember from this little drawing here that if you want to calculate an association constant using this old formula that you find in the 1982 paper of Attila Szabó, which relates the association constant to the potential of mean force through this equation here, which features, by the way, the Jacobian, which means that if you calculate what's APF, please hide the Jacobian on your PMF. Well, the framework in which you can use this expression is such that it assumes an orientationally average potential force, which would be the case here for these two dancing benzene molecules, the orientation of which spans the picosecond time scale. Typically, the orientation of benzene is from 6 to 12 picoseconds. The same, unfortunately, cannot be said for two interacting proteins. Unfortunately, you see a lot of studies in the literature of protein-protein binding affinity calculation based on a single potential amine force calculation, whereby they separated reversibly in a privileged direction the two proteins. Now, if you run a simulation of, so in this particular case, this is bar star interacting with barnase. If you run a simulation of bar star and barnase, or even just bar star, and you do a microsecond long simulation, you will not see tumbling of the protein. You will see like embryonic tumbling, just like the beginning of it. You do not see a complete reorientation. It's very slow. The time scale for the reorientation is very slow. But it doesn't mean that because you don't see it, you shouldn't take it into account in your estimate of the binding. If you really want to use this formula, you should really stick to its premises, which is this should be positionally and orientation average. So just like the protein ligand binding, our philosophy has been all the way. If you can't simulate it, if you can't sample it, then restrain it. And so it's exactly the same philosophy that we've seen for protein ligands. So we have the same equilibrium constants, except that in this case, instead of having ligand, we have bar star. It's a protein, but we say that it's bar star. But the difference here, for the reason that I mentioned previously, the perturbation induced by the disappearance of the ligand, of bar star, is so huge, and the reorganization of the solvent will be so substantial that it actually precludes using the alchemical route. So what we do instead is we resort to the geometric route, and we have the usual potential, the mean force, but in addition to, so you remember that in the case of protein ligand, we were just freezing by means of harmonic potential. We're just freezing the conformation of the ligand. You could extend that, freezing also the conformation of the protein. You suspect that there is conformational rearrangement of the protein on binding might happen. In the case of protein-protein interaction, we're actually freezing the backbone of both partners, but we're also freezing the side chain of the hotspot amino acids. The amino acids that are part of the interaction, of the interface. In the case of bar star barnase, the interaction stems from strong electrostatic interaction at the formation of a network of salt bridges at the interface, the protein-protein interface. This is all well documented. I think Alan Furch has worked on that for many years, and so there's tons of mutants, and we know what are the important amino acids. We know what the interface looks like. So we have here we have the backbone RMSD for bar star barnase, side chain RMSD, and then we have the usual Euler angles and polar angle. And of course, the restraints that we add on the conformation of the side chain and the backbone in the bound state, we also have to take them into account in the unbound state, which increases the number of PMF from 8 to 14 when you do protein-protein interaction. Let me show you why we need to actually have this extra potential for mean force, or this extra restraints and potential mean force calculation for the side chains. So when we started to work on bar star barnase binding, we were running this simulation, this separation. the main course of the calculation, with only restraints on the conformation of the backbone. We were not imposing any restraints on the side chain. And we were sampling and adding more sampling, and what we were seeing is the potential mean for the separation becoming shallower and shallower and shallower. And you can understand that from the fact that you're doing reversible separation. You're not pulling irreversibly, you're doing reversible separation a la ABF or a la sampling. And so you separate, and it comes back together. And as you do that, well, the soul bridges are disrupted in the reform. They are disrupted. But at some point, when they are disrupted, the side chains isomerize. And when the two proteins come back together, they don't find a partner anymore. Because, one of the chi angle has changed. And this potential mean for the separation potential mean force becoming shallower and shallower is just a reflection of the soul bridges not reforming. So we were losing one soul bridge, another soul bridge, to the extent that we were completely deteriorating. So it was extremely frustrating because you're adding more sampling, and usually when you add more sampling, you expect improvement. But in this case, we were just witnessing deterioration. Until we realized that, and we decided to add this extra restraint to make sure that when we separate reversibly, when the proteins are coming back together, they actually find a partner. And I think that with that, I will rest my case, inviting you to try this tutorial and do it the way you want. If you want to do it the lazy way, with the plugin that we just released, you're welcome to do that. If you want to do it as is explained in the tutorial with groups of people, one way or another is fine. And I'll be here at the time if you have any questions. We're good. This is copy break.
5 minutes left.
I think it's coffee break now, right?
1:20.
Hello? It's coffee break, right? Okay.
At 10:20, I have.
10:20? Oh, then we have
another
a bit more time. We can take some questions, yeah, sure. So, yeah.
Very nice talk.
Thanks.
First of all, I would like to say that. The second, everything you mentioned today depends that you know the binding site.
Yes.
If you do not know the binding site,
then you're pretty much doomed, because then you're running these very expensive calculations for nothing. You're basically shooting in the dark. That's a very good point. But then I can have a sharp retort for that. A la Benoit Roux, I can say that maybe you can think of this method as discriminating. So you start with a docking pause, and maybe you can use this method to discriminate between binding pause coming from docking procedures. Now, of course, to not completely be in the dark, it would be nice to have some ITC measurements. But the hope is that at some point this method will be, how would you say, robust enough that it could be potentially emancipated from the need of having the crystal structure.
So, like, do the relative one, the relative method that you mentioned.
No, actually, you get the absolute binding free energy and.
To discriminate between the different sites.
Yes,
and
exactly.
then zoom in on the one that.
For instance. Any other question? Yeah.
So you basically use the orientation quaternion formalism and basically converted that into Euler angles.
Yes.
You could have probably just used the quaternion as like quaternion.
Sounds like a deja vu. Sounds like a deja vu conversation. We need to really talk about that,
yeah, okay.
because I mean, I gave a lot of thought about it, and yeah, so okay, so kind of a private joke. The way we do it with this new variable that we introduced last year to make our lives easier to avoid this. Well, there are two reasons that why the hell did we go to this new variable? Well, one thing is to make your life easier, but also to prevent you from hitting snags. Depending on the shape of the ligand, it's very difficult sometimes to find or to create these groups of atoms that are such that you don't want the groups of atoms to be aligned. And there is a reason for that. You can hit what we call gimbal lock. And a gimbal lock, when you deal with Euler angles, is like an underdetermination of these Euler angles. So they're not properly defined. You're not completely sampling the orientational space. So you're missing part of the orientational space. And in principle, these new variables, which obviate the need of creating these frames of reference in groups of atoms, well, they are designed to avoid this gimbal locks. So that's one thing. The other thing is when we define this variable, so they come from a scripted function, and the actual call vars that we're using is orientation. And orientation returns a quaternion. So a quaternion is a mathematical object made of four numbers, four scalars. And we use these scalars, we use linear combinations of these scalars to return to the Euler angles. And in other words, to return to the original framework of Gunbart, Roux, and Chipot, 2013, for the post-treatment. So basically, then we calculate the potential of B-force over phi, psi, and theta. What Mahmoud is suggesting is we calculate the potential of mean force just from the quaternion, right?
Or the orientation angle probably would be enough. Orientation angle basically counts for any deviation.
So basically, it's doing one potential of mean force instead of three.
With the orientation angle. And that should cover everything at least, but we can think about it.
Yeah. It may be more elegant. In terms of saving you time, those PMFs, I mean, let's face it, they are dirt cheap compared to the separation PMF in the RMSD. But I agree. I mean, if we can make things even more elegant, we should do it. I mean, it's, yeah, if I had a caveat enter here, is those orientation PMFs and polar angle PMF, they're very, very cheap compared to the RMSD. Usually, in a matter of a few nanoseconds, they are converged. I mean, they are quadratic in nature. And whereas the RMSD, for the reasons of degeneracy that I had mentioned, for the separation PMF, is for everyone. We good?